Inside a modern substation, a 10 megavolt ampere 33 kilovolt to 3.3 kilovolt delta Y transformer operates in a state of continuous thermal and electrical equilibrium. It routes enough power to supply a small city, flawlessly stepping down grid voltage 24 hours a day. But an internal insulation breakdown, even a microscopic phase-to-phase short, shatters that equilibrium. The fault provides a path of least resistance, pulling an immediate, violent spike in current directly through the transformer's copper core. This animation of the transformer windings shows the immediate physical consequence of that fault. The heat generated within these coils expands according to the equation I squared R. Thermal stress does not scale linearly. It multiplies by the square of the fault current, turning electrical energy into destructive heat in milliseconds. If this fault draws current for even a few seconds, the heat load will melt the copper windings, decompose the insulating oil into highly volatile gases, and severely warp the mechanical structure of the core. To prevent this total equipment loss, protective relays must monitor the power flow and isolate the transformer from the broader grid almost instantly. But speed introduces a massive engineering tension. The protection system must be hyper-responsive to genuine faults, yet entirely selective, completely ignoring the harmless temporary surges in current that occur when large industrial loads come online. The first layer is a calibrated electrical matrix, a network of sensors calculating exact phase and earth fault thresholds. The second layer steps outside the electrical domain entirely. It uses a hydromechanical failsafe, the Buchholz relay, to detect the physical byproducts of internal degradation. Unprotected faults are violent thermal events requiring a multi-physics, highly calibrated shield to prevent the destruction of the unit and hazards associated with oil decomposition. We can build this electrical protection scheme from scratch using our 10 MVA transformer as the baseline. This layout shows the primary step, determining the transformer's normal operating ceiling by calculating its primary full load current, or FLC. We find this using the standard three-phase power relationship. We input the transformer's rated power of 10,000 kilovolt amperes, divided by √3, and multiply by the 33,000 volt primary rating. This resolves to a normal continuous flow of roughly 175 amps on the primary side. A protective relay cannot be set to trigger exactly at 175 amps. The grid naturally fluctuates. We have to calculate a pickup current threshold that sits high enough above the normal operating range to ignore transient surges, but low enough to catch a true fault. For the primary overcurrent setting, we set the pickup at 140% of the full load current. That establishes our true fault threshold at 245 amps. The protective relay microprocessors sitting in the control room cannot physically handle 245 amps. We use a current transformer, or CT, clamped onto the line to magnetically step that power down to a safe proportional level. We apply a common CT ratio of 200 to 5 amps. This means for every 200 amps passing through the primary grid line, exactly 5 amps are sent to the relay. We take our 245 amp threshold, multiply it by 5, and divide by 200. The math gives us 6.125 amps. This tiny secondary current is the precise electrical value that will physically hit the relay and trigger the circuit breaker to trip. By utilizing precise proportional scaling, engineers translate massive, lethal primary grid forces into highly manageable secondary trigger values. Establishing the trip threshold only solves the first half of the problem. A single fault will send high current through multiple relays across the grid. To prevent the entire network from blacking out, these relays must act in a strict time-based hierarchy. This time-current coordination graph illustrates the logic of an inverse time over current relay. The relationship is strictly inversely proportional. The larger the incoming fault current on the x-axis, the faster the relay trips on the y-axis. We first plot the curve for a downstream feeder breaker. This establishes the baseline response time for any protective devices located further out in the local network. We then plot the transformer's primary relay curve above that downstream breaker. We intentionally configure a time multiplier setting to create a gradient of 0.3 to 0.5 seconds between the two curves at any given fault current. This delay forces the system into a cooperative sequence. It gives the downstream device a fraction of a second to clear a local fault first. The transformer relay waits, preserving power for the rest of the grid, stepping in only if the downstream breaker fails. However, overcurrent relays have a critical blind spot: earth faults occurring near the neutral point of a grounded Y winding. If a phase conductor makes contact with grounded equipment, it routes massive current directly into the earth. But because of where the fault sits on the winding, the current registering on the phase lines remains very low, keeping it completely hidden below our 245 amp phase pickup setting. To detect this, we calculate an independent earth fault setting. Because normal earth current should be near zero, we tighten the sensitivity dramatically to just 20% of rated current. This gives us a primary threshold of only 35 amps, which scales down to a tiny 0.875 amp secondary trigger at the relay. By utilizing layered time current curves and tight earth fault thresholds, the transformer acts as a selective cooperative node in the power grid, targeting specific anomalies rather than reacting blindly to every surge. Even with perfect mathematics, the electrical matrix has an ultimate limitation. Current transformers only measure current leaving the tank. They are completely blind to low current internal degradation, like the slow breakdown of core bolt insulation. This blind spot requires a shift from electronics to fluid dynamics. Enter the Buchholz relay, a purely mechanical failsafe mounted outside the main transformer body. Its placement is highly specific. It must sit exactly on the pipe connecting the main oil tank to the expansion conservator, pitched upward at an angle between 2 and 5 degrees. The relay is built for harsh environments, utilizing a heavy-duty cast aluminum body with dual mounting flanges to integrate directly into the oil flow path. The front features a calibrated inspection window. The vertical graduated scale etched onto the glass is designed to measure the exact cubic volume of gas accumulating inside the chamber. The relay operates on a simple physical law. Every internal electrical fault decomposes the transformer's solid paper or liquid oil insulation. That chemical breakdown generates either slow gas bubbles or violent pressure waves. This diagram shows an incipient fault. As insulation slowly cooks, gas bubbles travel up the sloped pipe and rise into the relay. The trapped gas displaces the oil, causing the upper internal float to drop. This mechanical action closes an isolated magnetic reed switch, sending an alarm to the control room. In the event of a severe internal short circuit, gas generation is explosive. It forces a massive, violent oil surge through the pipe toward the conservator, typically reaching speeds over 100 centimeters per second. This oil surge slams directly into a lower baffle flap. The kinetic force pushes the flap backward, instantly closing the second magnetic switch. This bypasses all electrical time delays, directly tripping the breaker to save the transformer. By translating the chemical breakdown of insulation into kinetic, mechanical triggers, the Buchholz relay provides a tier of fail-safe security that purely electrical sensors cannot achieve. Once the Buchholz relay trips and the transformer is disconnected, the emergency is contained, but the investigation begins. Engineers must determine exactly what burned inside the sealed, multi-ton tank. Because the relay trapped the fault gases, crews use a specialized sampling device to extract the trapped vapors without atmospheric contamination. Using precise metal petcock valves and inspection windows, technicians carefully bleed the hazardous gas into the sampler. This sample undergoes chemical forensics. The extracted gas is pumped into an analyzer, where it reacts to specific testing chemicals to form colored precipitates, identifying the exact point of internal failure. If the analysis reveals a white gas that slowly turns brown under light exposure, it indicates that electrical arcing occurred directly against the paper or cotton insulation wrapped around the windings. A yellow gas points to the degradation of structural wood or cardboard supports. A grayish gas proves a breakdown occurred within the magnetic core laminations. The most severe diagnostic finding is a black gas. This confirms that free electrical arcing erupted directly within the insulating oil itself, signaling massive internal destruction. The security of the grid relies on these layered systems working together in fractions of a second: the precise scaling of current transformers, the strategic coordination of time delays, and the physical failsafes monitoring fluid dynamics. Effective transformer protection integrates electrical mathematics and fluid dynamics to detect high current faults and incipient chemical breakdown, ensuring the continued stability of the power network.